Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series BSc Applied Electronics. Today we are dealing with the subject Semiconductor Devices and Integrated Circuit. Let's start with the Unit 1, Lecture 3. And the contents in the Unit 1 are, today we are discussing tunnel diode UJT LED. UJT in the sense unit junction transistor, LED is a type of diode, light emitting diode. Let's start with the tunnel diode. A tunnel diode is heavily doped PN junction diode, where it has a negative differential resistance in between two types of voltage. One is peak value voltage, another one is valley voltage. In between these two there is a negative differential voltage, in the sense as we increase the current there will be a decrease in the voltage, and the tunnel diode is also called as Esaki diode, who is a inventor of a tunnel effect in this kind of diode. We will observe from the figure the symbol of a regular diode. This is what the regular diode, and this is what the tunnel diode symbol. This is one of the type, and we can also write in this form. This is the VI characteristics of a regular diode, PN junction diode, and the tunnel diode. As I said, the definition says there will be a negative differential voltage in between two type of voltage. One is peak, this point is called peak value voltage, and this point is called valley voltage. In between these two there will be negative differential resistance. Let us discuss how we will get this negative differential resistance due to a tunnel effect. What is tunnel effect? So, let us start the tunnel effects operation. The principal concept of electron tunneling: before contact of the semiconductor with the P and N region and with the depletion and with the impurities, the energy band diagram will be like this. This is the conduction band, this is the valence band of the P type. We are assumed throughout this session we are observing, we can observe from the figure the energy band diagram before the contact of the P and N region and also the impurity. Here the upper portion is the conduction band. This is the upper line indicates the conduction band. This is the Fermi level. Fermi level is the indicates the energy of the forbidden gap. This is the Fermi level, and below this there is a valence band. This is a valence band, this is the conduction band. This is how the energy band diagram before the contact of the P, N and the impurities. After contacts, how it looks like this. The conduction band, it comes in this line and the valence band looks like this, but there is a tunnel in between these two P and N region. When it comes in contact there is a tunnel, we can observe this. The conduction band rise above, and here also the valence band, it will comes below from the P and N region. So, for from the Newtonian and quantum theory, what it says means the electron can't cross this barrier, because we need to cross this barrier the electron has the voltage E is equal to EB. If the potential of electron is more than the EB, then only it can cross a barrier. It can only pass the barrier if it is having a more energy than the barrier height. So, we need a more energy for electron to cross this barrier. That is what we are observing from this figure. For a thin barrier, what happens? For thin barrier, Newtonian mechanics still says that electrons cannot cross the barrier. Even for the thin barrier, look at this, we can observe from figure. For Newtonian mechanics, it says for a thin barrier also the electron can't cross the barrier. If E is equal to EB also it can't. But it comes to quantum mechanics, it says the tunneling is caused the wave nature of electrons to cross the barrier. If the barrier is thin, the quantum mechanics says the electron can carry, only of it has a wave like nature, it can cross the barrier. This is what the quantum and Newtonian mechanics says if the barrier is thin. Then we comes to electron tunneling in p-n junction. How the tunneling will happens? Again we need to discuss with the energy band diagram. If the barrier is thick depletion, having a thick depletion layer, and it is high doping thin depletion layer. These are the two different figures we are observing. If it is thick depletion layer, we can observe there is a wider gap between the conduction and valence band, and if it is a high doping thin depletion layer, there is a narrow gap between the conduction and valence band. When the p and n region are heavily doped, the depletion region becomes very thin. So, when it is highly doped means the depletion layer is thin, so that we can expect the electrons can cross this thin barrier according to our quantum mechanics. What I said, if the electrons will have the wave-like nature and it is having a thin depletion layer, it can cross this barrier. During the tunneling, the particle energy does not change. This is what we call as a tunneling, and during this process the particle energy will not change. Next we move on to tunnel diode operation. Let us see what happens in a different bias mode. Under forward bias, first we consider step 1 with at a 0 bias there is no current flow. We discussed a normal p-n junction. In a 0 bias there will be no current flow, because the electrons won't move from the conduction band to valence band. So, there will be no conduction of current. When the semiconductor is very highly doped, the depletion layer will be thin. As I said, this is the Fermi band, Fermi level, and this is the conduction band, this is the valence band. In between this, if we have doped heavily, there will be a very narrow gap in the depletion layer, and at a 0 bias there is no current flows, that VI characteristics will be in 0, the current and voltage will merge to 0. Step 2, next we come to, if we apply small forward bias is applied, the potential barrier is still very high, no noticeable injection and forward current through the junction. We can observe in the graph there is a small current. This small current we can observe, this is due to the minority carriers. So, we can observe this small current here, but when we apply only small voltage we can observe this. If we apply very high voltage, we can expect more current. With a large voltage, the energy of the majority of electrons in the n region is equal to that of the empty states in the valence band. This will produce maximum tunnel current. So, that is what, when we reach a certain voltage, that is what we call as cut-in voltage. If we reach or if we cross this cut-in voltage, there is enough energy for the electron to cross the barrier, and this electrons will occupy the empty states in the p region, and we have a high current. We can observe from the graph where the current is increasing and electrons is moving from the this conduction band of the n region to the valence band of the p region. Next, step 4, as a forward bias continues to increase, the number of electrons in the n side that are directly opposed to the empty states in the valence band decreases. So, there will be a decrease, because when we are going to give a potential higher than the cut-in voltage, electron will crosses from the n region to p region, it will moving in the opposite direction. So, this will decreases a current. So, the tunneling current starts for decreasing from this peak point to here, like this it will going to decrease. This is called as direct tunneling current decrease. And next, in the step 5, what will happen is, as more forward voltage is applied, the tunneling current drops to 0, but the regular diode, what happens, if we increase the voltage, the current will also increases. But in the tunnel diode, we observe that if we increase the voltage for certain extent, it will increase, after that it will drops. But the more regular diode, forward current due to electron hole injection increases due to lower potential barrier. As we increase the voltage in tunnel diode, the depletion layer increases, so the electrons can't cross the junction. So, there will be a decrease in the current here, which we can observe in the graph. With further voltage increases, the tunnel diode IV character is similar to that of a regular PN junction. Again, after reaching certain voltage, again it start rising. After reaching certain voltage, the current is decreased. After this point, again it start rising when we increase the voltage. This is how the tunnel operation takes place in a operation of the tunnel diode. Then we move on to circuit. What are the things we will observe from the waveform? This point, it is strongly non-linear as compared to resistance, because it is not linear. When we change the current, it not vary according to the varying of voltage, but there is a increase and also decrease of current. So, we can define this peak point of voltage as a peak voltage, and there is a very low voltage is called as valley voltage. And also in between this, as from the definition we come to know there is a negative resistance region. This is how we will get the negative resistance region for a tunnel diode. And 0.07 voltage is mentioned here because silicon semiconductor we are used. It is a 0.7, it has to be. This is the cut-in or barrier potential of a silicon, that is why it is 0.7 mentioned here. And the peak voltage is a 0.07 voltage, and this is the cut-in voltage, that is 0.7 voltage, valley voltage, also called as valley voltage. Next, let us discuss some of the expression that we can observe from the curve, and we can get some of the expression. What are the expression? The total current I in a tunnel can be expressed as I is equal to I tunnel plus I diode plus I excess. What is I diode? I diode means when we operate as a normal PN junction diode, this current is taken as I diode, and this current is taken as I tunnel. This current is taken as high current, and this current is taken as I excess. In saturation current and the PN junction current is I diode, that is Is exponential of V by eta Vth minus 1. Here eta is equal to Kt divided by Q, where K is a Boltz's constant and T is a temperature in Kelvin and Q is a electron charge. Then tunnel current. Tunnel current is expressed as V by R naught into exponential of minus V by V naught whole power m, and where m is equal to 1 to 3 and V naught is equal to 0.1 to 0.5 volts, and R naught is the tunnel diode resistance in the ohmic region. The maximum negative differential resistance can be found as, this is the expression for maximum negative differential resistance. RD max is equal to R naught into exponential of 1 by m whole by m, and the peak voltage Vp is equal to 1 by m whole power 1 by m into V naught. Next we move to excess current. Before going to excess current, we will have a short break. Welcome back. Let us see what is the expression for excess current. The excess current is expressed as V by RV exponential of V minus VV divided by VEX. Here IXS is an additional tunneling current related to parasitic tunneling via impurities. The impurities that we are added, no, due to that there is a parasitic tunneling. Due to that we will get this excess current. This current usually determines the minimum current, that is what I said, this is the minimum current. This we called as an IXS. This is a minimum current, this we called as an IXS. IV. RV and VXS are the empirical parameters in the high quality diodes. RV is very much greater than R naught and VEX is equal to I to 5 volts. Then we move on to applications of tunnel diode. Tunnel diode can be used as high frequency oscillator as a transition between the high electrical conductivity is very rapid. So, we can use this in a high frequency oscillator circuit, and it also used in a microwave circuits. Tunnel diodes are resistant to the effect of magnetic field, high temperature and radioactivity. So, it can be used in a many modern military equipments. These are used in nuclear magnetic resource machines, and also its very much used in a satellite communication equipments. Next we move on to another type of transistor. We are come across till now diode. We move on to one of the type of transistor, UJT. UJT stands for uni-junction transistor because it has only one junction and it has 3 terminal, because the transistor should have 3 terminals and it is having only one junction. It is called as uni-junction transistor. Let us see how it looks like. In uni-junction transistor, there will be one junction, that is P and N. In between that there is a junction. Here P is heavily doped and N is lightly doped, and this where P region having a single terminal called as emitter and N region having 2 opposite terminal. There is a 2 terminal in the N type region, that is base 2 and base 1, also called as B1 and B2. Biasing of UJT unijunction transistor is always operating with a forward bias voltage. For this purpose, the emitter bias 1 junction, that is emitter bias base 1 junction is always kept forward with respect to base 2. This emitter and base 1 is always kept in forward condition for operating with respect to base 2. This is how we are going to bias the unijunction transistor for in a forward bias mode. How it operates? Let us see how the unijunction transistor operates. It operates in both forward and reverse bias. Look into the circuit. What we observe means, once when we give applied a voltage, this E1, this E terminal, that is emitter terminal and base terminal will going to short circuit if we give a positive voltage, and if it is in a forward bias mode, this E and B1 will going to short and current will conduct. And also the potential or external voltage is 0. If we did not give any voltage, then this E and B1 will be open circuit, there will be no flow of current. The direction of current is shown here, because we are taking the unijunction will be operates in forward bias only when E and B1 is shorted with respect to B2. It is so because the holes of heavily doped P type region are entered in the N type bar and recombine with the electrons. That is why we are going to observe this kind of forward bias only in between E and B1 terminal. Means we know that this P is heavily doped and N is lightly doped. The electrons are moving from the N region to P, so the current is flowing from E terminal to B1. That is why we can expect the forward bias mode when the E and B1 is shorted. Next we move to application of UJT. These are used to make a simple oscillator, because if we use this UJT with few number of passive devices, we can get some oscillator circuits. So UJT can also be used to measure magnetic flux. This is one of the important application where we are going to measure the magnetic flux. We are using the UJT. And next we are moving to last topic of this unit, LED, that is light emitting diode. We have seen in many ways the light emitting diode, but we do not know what it is, how it works. Let us know how it works and what it is. LED means light emitting diode or semiconductor PN junctions that under forward bias condition can emit radiation, and that radiation falls in a visible light wavelength which is in the electromagnetic spectrum, so that it is visible for a human eye. When it is in the forward bias condition, it will going to emit a radiation that falls in the visible bandwidth of in the electromagnetic spectrum, and the quanta of light energy is emitted is approximately proportional to the band gap of semiconductor. The band gap of semiconductor will depend on energy, that energy of the light that will going to emit, no, that light energy is depend upon the band gap. And the symbol of the LED is it looks like a normal diode, but with a 2 hallmark. This is like a light rays, that emitting light rays, visible light rays, and this is anode terminal, this is cathode terminal. The direction of current is like this, from anode to cathode. Let us see how does it works. It works like as a simple PN junction diode, but what we are going to use here is a material that we are going to use to make LEDs different. Usually we are going to use indium, gallium, arsenic and phosphor combination of materials to get an LED, because in PN junction also when the recombination takes place, the light will emit, the energy or rays will emit, but that is not a visible light. We need to get a visible light, so we are using a different material to make LED. During the process, typical LED needs a PN junction. As I said, P type material will be there and N type material will be there like this, and in the N type there will be a majority carrier of electrons is present, and in the P type majority carrier holes are present, and the energy band spectrum, it looks like this. Energy band diagram looks like this. This is the valence band of the N type region, this is the valence band of the P type region, this is the conduction band of P type region, and this is the conduction band of this dotted line shows a Fermi level. When the recombination takes place, that is when the electrons from N region moves from the conduction band of the N type region to the valence band of the P type region, there is a emission of light. You can observe there is a emission of light. This emission of light is a visible light. That is how we will get the LED glow. This is how we can say the LED works due to the recombination process. The recombination process means when the electron move from the conduction band of N type material to the valence band of the P type material, it releases a light. That light glows a LED. This is how the LED works. Next we move to merits of LED. As we know, we are using many applications LED in electronic devices and also in many applications. Why we are going to use? Because it have lots of merits. One of the merit is longevity, efficiency, and it has a cost, it is very cheaper, and it is robustness and greater light intensity. It is very small in size. All these merits will make it to use in many applications. Why it is long? It is the light emitting elements in diode is a small conductor chip rather than a filament, which greatly extend the diode's life, because the light emitting element is there in the diode. No, it is a very small conductor chip. It is not like a filament bulb that what we are going to use. It doesn't last for long. But here the light emitting material is, it is very small chip. That chip will going to last for long, and also it emits a light having very high intensity. So it is having a greater light intensity, and diodes emit almost no heat and run at very low amperes. So it requires very less voltage to operate and it operates in very low amperes. So that is why it is called as efficient. It is not too costly also, and it is robustness, since solid state components not fragile as incandescent light bulbs. So these are the merits of LED. Now we come to the summary. In tunnel diode, what we discussed: tunneling, what is a tunneling, how the tunneling will happen in the tunneling diode, and what are the working principle, how we get that negative differential resistance, what is the peak voltage and what is the valley voltage, what are the expression of a current in tunneling diode. All this we discussed. What is UJT, how it works, everything we come to know from UJT section. And after that, the last topic is LED, light emitting diode, how it works and what are the merits, application. All this we come to know from the LED part. And we need to observe one thing, that is the tunnel diode or the UJT and also the LED applications, or whatever the topic we discussed today, all these operates in forward bias, that is in a forward mode we are going to use, and we are going to use in an application. This is what the summary concludes. And next is some of the questions is: what is tunneling, what is NDR, negative differential resistance, peak voltage, valley voltage, and how does UJT works, how does LED works. These are some questions. Further reading, you can refer these two websites and also the textbook Electronic Devices and Circuits by GK Mittal. This ends up the session. Thank you.